right, so you just looked at an image of light pollution in North America. And if you Google light pollution, you can pull up maps of light pollution all over the world. Very fascinating stuff. Like, how did you know that you were looking at California? Or what can you tell even from my image that you're looking at California?
Because there are certain spots with lots of lights, which I can recognize where they are, and other places which...
How do you recognize it? Like, what's that?
This is San Diego, and this would probably be LA.
Okay,
yeah.
So he's doing what probably many of you did when you first saw that image. You're like, yeah, that's cluster right there. It's probably San Diego, and then that's probably Chicago over there, and we got the tri-state area, right? We can definitely pick out major metropolitan areas by the number of lights. So if you were looking for love, right, you're kind of young, but if you were looking for love, where would you head and why?
I would head to New York, New Jersey, because there being a lot of lights means there being lots of houses, which likely means there is more people.
So you're going to be very picky? That's why you need a lot of people to choose from?
No.
Just kidding. But but you wouldn't want to head, right? You're driving around, there's no more coronavirus. You're not going to head to this part of the country where it's all dark, right? Because as my son stated, right, there's not that many houses out there. There's not that many lights, so there's not that many houses, which means there's probably not that many people. However, we can't be guaranteed just because we go to an area with lots of lights that we're going to encounter a person, right? Someone could have all the lights on in their house and not be home at all. So we just have a better chance of finding a person if we go to an area where there's a lot of lights. All right, so we just looked at a map of light pollution or lights in the middle of the night, right? And we talked about how if you head towards a bright area, there's a pretty good chance that you're going to find a person. Well, I want you to start thinking of orbitals like probability distribution maps. Orbitals usually see like a nice, well-defined shape. When we discuss orbitals, we have a big spherical one. This is our p orbital. But this is not really what it looks like. What it actually looks like is one of those maps. And so there's a bunch of little dots representing the probability of finding an electron. So where there's more dots, we have, so if it's super dark in here, kind of like on that map of the United States where we saw a lot of lights, that means there's a higher probability of finding an electron. It's a little bit lighter. The dots are not as dense. So over here, like it's less dense, less dots. Then there's going to be a lower probability of finding that electron. And then we do have areas, and this is where this line comes from, right? We have areas where there's no dots. So there's absolutely no probability of finding the electron over here. And so that's when somebody comes in and says, well, there's a 99% chance it'll be located within this region. Let me draw what the orbital looks like. But in reality, if we're going to draw it properly every single time, we should be drawing it like a probability distribution map. The quantum numbers, then, to go with like the math and the people analogy, we can think of quantum numbers as social security numbers for electrons. So back in the day, the beginning part of your social security number, and ask your parents about this. Mine, I'm 40, and this is how my social security number works. My siblings and I, we all have the same beginning digits to our social security number because we're all issued our social security numbers in New York. So back in the day, your social security number used to tell you, tell a person what part of the country you were from. And they've changed that because of identity theft, but you know, there's still enough of us with these location social security numbers. So one thing that the quantum numbers tells us is what type of orbital and what position of orbital is going to be called an orientation that we could potentially find that electron. So it gives us information about location, and we're going to go through all these details. And it also gives us information about the size of the orbital. So there's each orbital can be described by 3 quantum numbers. And that's specific to the orbital. So again, this orbital right here, this p orbital, has 3 quantum numbers associated with it. Within this p orbital, there's only going to be 2 electrons. And it doesn't matter what, if it's an s orbital, p, a d, an f, each orbital only holds 2 electrons. So since each electron needs its own social security number, it needs its own quantum number, then we throw a 4th number on there so we can distinguish between the 2 electrons in this same orbital. So the first 3 numbers are going to be exactly the same for those 2 electrons, and then they're only going to be different by that 4th number. So we have one more quantum number that allows us to distinguish between the 2 electrons. It's called the spin number. And again, we'll go through that in a different lecture. Alrighty, so I want to start introducing the quantum numbers before we talk about the shapes of the different orbitals. And that way, hopefully, everyone can make the connection between the quantum number and the orbital shape. So to do that, we're going to do the first 2 types of quantum numbers. So the first 2 rows on page 16. So the first thing is the principal quantum number. This is your n value, represented by n. And this describes the size of the orbital. It also describes the energy level of the orbital. So what happens, n starts at 1, n equals 1, n equals 2, n equals 3. As n increases, both energy and size increase. Determining n is not too bad. We just use the row of the periodic table. So if you're in the first row, you're going to have 1s orbitals. And then when you're in the second row, you have 2s, and then you also get 2p orbitals. But there's going to be a pretty decent correspondence between the row of the periodic table and your principal quantum number. The next one is our angular momentum quantum number. And this is going to be symbolized by a script L. And this describes the shape of the orbital. to determine the L value, the angular momentum quantum number. And when students have like in-class exams, I always encourage them, write this at the top of your paper, right when you get your exam, right? It's going to be S, P, D, F. Like a PDF, but starts with S. So these are going to be your orbitals. And this is what we're going to discuss in just a second, what S, P, D, and F look like. But we use numbers to describe them. So L is going to be, the L value for our S orbital is 0, P will be 1, D will be 2, and F will be 3. They haven't discovered elements that use anything beyond the F orbital. However, there's theories that it's possible, and so they preemptively name them like G, H, I, and so these are at this point theoretical. But then the numbers would do the same. So just continue 0, 1, 2, 3, 4, 5, 6, and so on and so forth. Alrighty, let's look at the last two quantum numbers. So we have the magnetic quantum number, which is symbolized by M subscript L. And this describes the orientation of our orbital. So we could say the position, but more commonly, it's referred to as orientation. And this part will make a little bit more sense when we go through the S, P, and D orbitals in more detail. How do you know how many different positions or orientations something can have? So there's a formula. The number of orientations equals 2L plus 1, where L references the angular momentum number. So for instance, let's do an example because I know this is difficult if we leave it at that. So an example, say we're talking about a p orbital. We know that the p orbital has an L value of 1. So then we're going to take that 1 and plug it back into here. So the number of orientations then is equal to 2 times 1 plus 1. So we come up with 3 different orientations for our p orbital. And indeed, again, as we start connecting all the pieces, that's what we'll see. You might remember from drawing electron configurations that there's 3 lines or 3 orbitals for p. And specifically, they're aligned along the x-axis, the y-axis, and the z-axis. So I put little subscripts, our x, our y, and z. We're going to assign numbers around 0. So that's one of the things that I like to write on this table is that the numbers for ML are centered around 0. So if we decide that something has 3 orientations, or we calculate that, then my numbers then would be -1, 0, and +1. And these numbers, the -1, the 0, and the +1, are the actual ML values. It's not the 3. The 3 tells us how many numbers we should be writing down. It's these numbers here. Big picture wise, And again, all of these things connect, and I always struggle every semester. Which order should I teach them in? Electron configurations. So if you remember that, and if you don't worry, we're going to go over it again. S has one line, which means it has one orientation. So your ML value for S is 0. For P, it has 3 lines. So we're looking at -1, 0, +1. For D, it's 5. So the ML values are going to range between -2 and +2. And then for F, it's going to be 7. So we're looking at ML values from -3 to +3. All right, so continuing on to the spin quantum number, that's going to be the one that's for the electron, and it's M subscript S. It describes the spin on our electron. Remember, they're both in the same orbital. These orbitals hold 2 electrons. Again, relating it back to electron configurations, if you had an s orbital, you would draw one arrow pointing up and one arrow pointing down. And that's, you're looking at the spin quantum number right there when you do that. They don't go up or down. They go clockwise or counterclockwise. And if one flips, like due to the presence of a magnetic field or something, if this guy is spinning clockwise and all of a sudden it starts spinning counterclockwise, then that induces the other electron in the orbital to spin the opposite way. It's a super cool theory, and this, if you're interested, it gets on like the edge of like the subatomic particles and all of that work. This is the beginning of it with Pauli and the Pauli exclusion principle and all that. I digress. How to calculate? It's one of the easiest ones to calculate. There's only 2 possibilities. It's going to be +1/2 or -1/2. We don't know. And I also raised something over here. Again, don't think that you can directly connect it. So we don't know that +1/2 is this guy. It's a very arbitrary assignment. We're just trying to say that they're each unique. So whatever +1/2 or -1/2, if there's 2 of them, we have to have both of these numbers. But if you have an orbital with just 1 electron, then it's totally up to you. You could pick +1/2 or you could pick -1/2 because it's an arbitrary assignment. So just a quick summary, you might want to squeeze this information underneath the names of each quantum number in the first column. Your principal quantum number is your shell. So if you're looking at a more traditional model, like the Bohr model, typically those rings are considered shells. So you have your first shell, your second shell, your third shell, so on and so forth. And then you have your angular momentum quantum number, which is known as your subshell. And then that's going to be specific or give information about the shape of the orbital. Next, we have the magnetic quantum number, which is about the orientation. So at this point, we're at an individual orbital. So the shell can potentially contain many different shapes of orbitals. It can be S, P, D, F. One shell can contain all those shapes. When we get to the subshell, then we're limiting our discussion. We know which orbital we're in. We're in an S orbital specifically if our L value is 0. By the time we get down here, we know which orientation we're talking about. So we're pinpointing not just the shape of the orbital, but a specific orbital within that shape. And then finally, the spin quantum number pinpoints an individual electron.